The idea of capturing CO2 for the primary goal of removing it from atmosphere is not a new concept. It goes back to the 1970s. The first CO2 pipeline was actually built in the US in the 1970s. So far, it's fair to say that carbon capture has not lived to its promise. But we are seeing lately, since 2020, a new dynamic. CCUS, as we call it now, is regaining a momentum. There's further realization that without CCUS, the energy transition and the climate targets by 2050 will become more challenging. And as part of this, CCUS is seen as a key enabler of making hydrogen happen at scale. The deployment of CCUS on an industrial scale will require CO2 pipeline transportation. This is a weak link in the value chain, and the Global CCS Institute estimates that the transportation infrastructure will need to be 100 times more than current. If we consider the current issues in building new pipelines, the repurposing of existing hydrocarbon pipelines for CO2 transportation will be a major facet of building this infrastructure. We need to first address internal time-dependent trait mechanisms, which could lead to a loss of containment, mainly internal corrosion and also stress corrosion cracking, depending on the impurities. If we are dealing with CO2 from steam methane reforming plants, we need to consider the presence of impurities such as hydrogen sulfide, carbon monoxide, and hydrogen. And we will need to consider for cracking and carbon monoxide CO2 stress corrosion cracking. This mechanism can be very severe in a CO2 pipeline. However, they can be managed by preventing the presence of liquid water and enforcing suitable water specification limits. Still upsets can be possible. We need to have quantified this mechanism adequately and to have proper integrity management practices in place to ensure corrective measures remain effective. Finally, and not least, we need to address the topic of fracture propagation control. We need to have a good understanding of materials, DNA, and properties, particularly that of fracture toughness across our pipeline. When we look at the experience we have from the US CO2 pipelines, it is very positive. The number of incidents has been very low. None were internal corrosion related, and no long-running fracture propagation incidents were reported. But we need to apply caution here. The USA pipelines are mostly transporting CO2 from natural sources for enhanced oil recovery. That means that the carbon dioxide is relatively pure, and this implies that defining water specification for such product is not too complex a problem. This is not a benefit that will be offered for CO2 originating from process plants and from steam methane reforming process plants. We will also have to observe that we may have to deal with complex pipeline clusters involving multiple feeders. And in this case of configurations, we could expect upsets. In regards to fracture control, the US CO2 pipelines were mainly built with crack arrestors, as high toughness line pipe materials were not available at the time of construction. Retrofitting crack arrestors on existing pipelines will not be the preferred option. It will be costly, and this method does not assure short fracture lengths. First, a good understanding of the integrity baseline condition is a must. The ideal business scenario would be to operate CO2 pipelines in the dense phase. We have to look at operational stresses much higher than what we have had in previous services. So we will need to consider the impact of this on existing flows, metal losses, and cracks to confirm the MAOP. Understanding existing traits from historical services will be also important to deploy the most cost-effective and pragmatic inspection strategies to obtain a representative picture of the pipeline's pre-conversion. Finally, we will need to have a good understanding of our pipeline materials, DNA, and fracture toughness. If we deal with vintage oil lines where material documentation is not available or incomplete, the deployment of smart, intelligent material sampling strategies will be needed to achieve a representative picture of the line. Our integrated team has developed a conversion roadmap to help pipeline duty holders to safely repurpose their pipeline assets to CO2 service. Yes, inline inspection in CO2 pipelines are possible and they are necessary. We need information of material populations to drive our material sampling strategies for fracture toughness testing more intelligently. Inspection technologies such as ROMAT PGS can help us targeting this information for conversion projects. Secondly, the occurrence of time-dependent traits could be very severe, even transiently, and this would require the pipeline condition to be regularly monitored by metallurgists and crack detection tools to ensure control measures remain effective. Finally, other technologies such as geometric and bending strain tools will be required as part of the general pipeline integrity management programs. As a final note, there are challenges to deploy inline inspections in CO2 streams, but they are not insurmountable through due engineering diligence. The ROSEN group has already successfully inspected CO2 pipelines.